Hello everyone, welcome to this video. In this video, we will build a model or simulate the operation of an induction motor. So here, as you see, MATLAB, let's say home page. So once you are on at home tab, so you select Simulink, you click on Simulink, then you click on blank model and create model, and then you will have this model where you can build the model. So you can go through the library to collect the components that we need. So if I go through the library, so here is the library, you go to Simscape. From Simscape, you select electrical, scroll down until specialized power systems. In specialized power systems, you select sources, for example, and we need to have a three-phase source. So here we have a three-phase source. So we drag it and drop it in our menu. So, or you can just double click anywhere in the model and type some words from the element or component that you want to have. For example, I want to have a measurement device, and this measurement device is a three-phase volt ampere measurement. So here is the device, and then after that, I need to have the power measurement device. So again, I'm typing of measurement, and I'm looking for power three-phase measurement device. So let me look for it. So here we have power measurement three-phase, and let me see. We have again, this is phasor. So what we need to have the instantaneous one. So again, power measurement three-phase. So let me double check with this one. Yes, so this is a power measurement three-phase continuous. Okay, so we can use this. Actually, I think we may have another one as well. So let me see whether we have it. So power three-phase phasor, it doesn't work here because we are solving in time domain, and here it is three-phase instantaneous. So you can use this or this, but this, as you see, the input is 1 voltage, either line or phase voltage, and here you will have one current, but here, as you see, you can have at the input the three set of voltages, the set of three voltages, and the set of the three currents. So let me use the one with the set of voltages and set of currents. Of course, we need to have some displays in order to show the results of all measurements. So we need to have the motor itself or the machine itself, and the machine itself is called the asynchronous. So an asynchronous machine, and as you see here, we have many of them. So we have SI units and we have pair units. So the one that we need is the SI unit. Okay, after that, we need to have more blocks like bus selector. So here is the bus selector. We need to have the gain. Here is the gain. We need to have a product block. Here is the product block. We need to have constant block. So constant block, here is the constant block. And what else we may need? We need to have a scope to show the waveforms. So here is the scope, and we need to have the power GUI, of course. So this is the power GUI. I guess that these are the elements that we need to have them. We can also have voltage measurement and current measurement as well. And of course, we need to have the RMS block. So let me also add here voltage measurement. And let me have also the RMS block. Okay, so this is the RMS block. Now I think these are all the components that we need to build this model. Okay, so let's start with the Power GUI. I will have it somewhere here at the corner. And as you know that for Power GUI, we don't do any connection. So it has no inputs and no outputs. And here we have the source. So for the source, so we need to double click on the source. And before have let's say updating the values of the source, so let's see what the rated values of the motors that we will have. So here we have two types of induction motors, so the wand motor or the squirrel cage. So we need to have the squirrel cage one. Okay, and we need to select one of the preset models. So let me select, for example, let me see, I will select the first one. So we are going with the first one. Okay, so I selected this model. So now I will do apply. And before, as you see here, we have the motor, and before going, making OK, clicking OK. So I want to see some parameters. So the voltage is 460 volts and the frequency is 60 hertz. So I'm doing OK, and now going to the source. So the source should be 460, and as you see, this is the phase to phase. So what I need to do here is 460. So 460 volts, and the frequency is 60 hertz. So we do have it. So I don't want to have any internal resistance. So you need to uncheck this box. And I think everything is okay now. As you see, we don't have any internal resistance. Okay, so I think now the source is already set. So we can now connect the source to the motor through the measurement device. So we can measure the voltage and the current. And here we have the motor connected to the measuring device. So here how we connected it. So A to A, B to B, and C to C. Okay. So now we need to apply torque to the motor. So we use the constant block. Sorry, we use this constant block. And in order to modify the value of the torque, we use a gain block. So this gain block will be used in order to modify the value of the torque applied to the motor. So now we need to see what is the value of the torque that we need to apply. Again, we type on the induction motor. So we see that it is 5 horsepower and the speed is 1750. So now we go here and we insert the value, which is 5 horsepower times 746, which is the number of watts in each horsepower. And we need now to divide this power by the speed in radian per second. But the speed that we have is 1750, which is in RPM. So we need to convert it to radian per second. So here we have 1750. And how to convert it to radian per second? I need to multiply by 2 pi and divide by 60 and divide by 60. So this is how we do the conversion of the power from, sorry, the conversion of the RPM to radian per second. So before I update this value, so let me double check whether we do correct calculation. So I'm going to MATLAB and I will paste that formula here, and I will see that the torque is 20 point something Newton meters, and this is actually the correct value. So I'm going back to my model, and now I will, let's say, make this block some how, let's say, longer, so I can see that value. And now I will paste the value that I calculated, and I will give the unit of the measurement in Newton meters. Okay, so now I have the torque set, and here we have full torque since the gain is 1. Now we bring the bus selector connected to the measurement side of the motor, so we can see the values. So now what values I need to do to extract from the bus selector? So you do double click. So you have signal 1, remove it, signal 2, again remove it, and now I want to add. So from rotor measurements, I need to have the voltage, current, so it's current, flux, voltage. I don't need anything from rotor measurement. From the stator measurement, I need to have one of the three-phase currents. So you have three of them, A, B, C. So one of them, because it's symmetrical system, so I will have one of them. So I will select it. So I have the stator current in phase A, and it is measured in amperes. And let me see what else I can have. I don't need all these parameters. From mechanical, I need to have the rotor speed. So I'm selecting it, and it is in radian per second. And I'm selecting also the induced torque. So this is the induced torque. So I'm done with this. So I'll click apply and then OK. So I can also make the selector a little bit longer, so I can, and it's see the outputs clearly. So one of the all these outputs should be connected to displays so we can see them. So this is the current, and since this is the current, it should be connected through an RMS block. Double check that the RMS block has the same frequency as it is for that machine. Okay, so now we have this. So now we can copy and paste the display several times because we need it to show all the values. So let me do it 3 times at this point. And now I'm connecting the other component, which is the rotor speed. Okay, and this rotor speed is in radian per second. So if I want to see it in it's in RPM, I need also to convert it. So let me copy this again, and then I will paste it. And here I'm pasting the gain, connecting it. And for this gain, it should be, so if omega is equal to n times 2 pi over 60, then n will be equal to omega times 60 divided by 2 pi. So it will be 60, and this will be divided by 2 pi. Of course, make sure that you have 2 pi in parentheses. Okay, so this will be just like this, and we, of course, we will double check the value. Okay, so I didn't click OK. Need to click apply and OK. Okay, so we will check the value once we run the model. Okay, so in order to see the output power, so the output power is the product of the torque applied to the machine and the velocity in radian per second. And the velocity in radian per second. So here is the velocity in radian per second. Okay, so this will be the output power, and let me also show it on a display. So this will be the output power, and let me also label it as P out, comma, and W. It's measured in watts. Okay, so this will be the output power. Now I want to measure the power, the input power. In order to measure the input power, I need to have the set of the three voltages and the set of the three currents, okay? So this is, and here I will have the output power, both the active power and the reactive power. So this will be copy, and here is paste. So this will be the input power, both the active and reactive. Okay, so let me do this like this, and this one just like this. Okay, now this will be P input, and comma, it will be in watts, and this will be Q input. It will be Q input, and the reactive power is measured in volt ampere reactive. So volt, ampere, and reactive. Okay, so in var. So this is for the output power. What else I can see? Also, I can see the voltages and the currents during starting. So if I also change the number of ports, so let me double click on the scope, and here you go to file, and then you have number of ports, make it 2. Okay, so now I can also see the voltages. Actually, I don't need to see the voltages, I need only to see the currents. Okay, so let me back, double click and the number of ports and make it back 1 port. Okay, so this is the scope that can show me the 3-phase current. So if I want to measure the voltage as well, the line voltage, so let me measure it here. So the line voltage, so I will measure the voltage between phase A and B. And again, I need to have a display. So let me have this display here. So this will be the voltage. And of course, I need again RMS block, because this voltage is AC voltage. So you need to measure the root mean square value. Okay, so this is the RMS block for the line voltage. So I believe everything is done. So let me see whether the model is correct and has no errors. So 1 second, I believe, is good for simulation time, and let me run the model. Okay, so what we see, so we have full load, as you see, and which is 5 horsepower. So the voltage is 450.6. So this is the line voltage between A and B. And we have the speed is 1758. 1758. Okay, so we didn't show the torque. So let me show the torque. So I need to have one more display copy. This is the induced torque, and I want to have it like this. So this is the induced torque. Okay, so let me take this a little bit below, and I will bring this display to be aligned with this. Okay, and let me do the time, or before doing the time, let me see the scope. Okay, so I see the starting current. So this is the starting current, and I see that 1 second is too much, so we can do it, for example, 0.2. Okay, so let me do it 0.2 seconds. Okay, so 0.2 seconds and run. Okay, so what I see that the voltage is 457, which is rated was given for 460. So we have some voltage drop. I see that the speed in RPM is 1758. So this is the rotor speed in RPM. I see that the current is around 6.5 ampere RMS. The induced torque is 21.54 Newton meters, which is more than the input torque to the machine, because we have rotational losses inside the machine. I see the output power is 3,748, and the input power is 4,198. So we can also here do the efficiency. So in order to do the efficiency, I need to have a divide block. So the divide block, so we will have P input in the bottom. So I'm taking P input, and the P output should be at the top. And here is P output, right? Okay, so let me do it like this. And now I need to have display. and this display will show the efficiency. Okay. Of course, we may have a gain to multiply it by 100%. So let me also copy again. So copy, and here I will paste it. So this is the gain. Okay, so it is not connected. So let me see whether I can yes, it's now connected. So I will take it like this, and I will make it a little bit nicer like this. Okay. So for this gain, it should be 100. So the efficiency will be measured in 100. Okay. So apply and okay. So now let me run the circuit again. So I see that the efficiency is 89.27%. Okay. And if you look to the current, so this is the starting current. We see that we have a three-phase, we have a starting current, which is 5 times the rated current, around 5 to 7 times the rated current. And then we have something around 10, which is the maximum value, which is in RMS will be 4 point something. We see also that the voltage is around 457, which is around 460, which is the applied voltage, 460, which is the applied voltage. Okay, so this is again the torque, applied torque. So you can, of course, change the torque by changing the gain here. For example, let me do it 0.8, which means that the motor is loaded by 80% of its normal load. And as you see, the speed will be higher a little bit because the load is less. The efficiency is 88.66. The power, output power, input power are less because the load is less. Again, you can see the three-phase currents during the starting. So these are the three-phase currents, okay? And here is the velocity in RPM. Of course, you can also calculate the power factor. So the power factor is P input divided by S input, the apparent power, and S is equal to the square root of P square plus Q square. So you calculate the apparent power as P square plus Q square under the square root, and then you divide P input by the apparent power. So this is how you can calculate it. And of course, in order to calculate the slip, so you need to deduct this number from 1800, which 1800 is the synchronous speed, and then divide it by 1800. So 1800 minus 1767 and divide it by 1800, and then you multiply it by 100%, so you can have the slip in percent. So this is the model of the squirrel cage three-phase induction motor. Thank you.